In this video, we're going to be talking about the law of conservation of mass and how it relates to balancing chemical equations. So the law of conservation of mass, also known as the law of conservation of matter, really just states that mass can neither be created nor destroyed. So what this means is that none of us are magicians. Nobody's a magician. Chemists are not magicians. When something undergoes a chemical reaction, that does not create an object or make an object disappear. Everything from that initial start of that reaction is present in the final products of the reaction, even if it's not obvious. If you actually weighed things out, if you weighed the mass of what you start with, no matter if you catch it on fire or anything, if you have it in an enclosed system and weigh everything at the start and everything at the end, then the mass will be the same. And not only is the mass the same, but actually specifically each element at the start of the chemical reaction will be the same, or the amount of each element at the start of each chemical reaction will equal the amount of each element at the end of the reaction. So not only do we have the same mass, but we also have the same elements. So we'll see an example in a minute, but you'll make sure that you have not only the same mass, but the same elements and the same number of each element, the same amount of each element. And so that brings me to the final bullet point. Since there is the same amount of each element at the beginning and end of the chemical reaction, the mass is the same at the beginning and the end of the chemical reactions. Because what's happening is it's the exact same element. It's not a different isotope of the same element. If we start with carbon-12 on one side of the reaction, that means on the other side of the reaction, we're going to still have carbon-12. We're going to have carbon that weighs the same. All carbon-12s weigh the exact same. So there's no changing of mass from even when the elements are the same. The same elements, same mass on both sides of a chemical equation. So let's look at what a balanced chemical equation kind of looks like. So here's an example of one. We have reactants on the left side and products on the right side. And you can think of it as the reactants are the things that are reacting in the chemical reaction. So at the start of the chemical reaction, what are we going to react? What's reacting to one another? And then the products, that's what you produce at the end of the reaction. So looking at this, we can see that we have methane reacting with oxygen to form carbon dioxide and water. So methane, if we want to look at it in more looking at the direct chemicals, we can see that we have one carbon here, and let's go ahead and count this all out. So I have here are the different elements that I have in this balanced chemical equation. I have carbon, I have hydrogen, and I have oxygen. And then since we said that everything's going to be balanced, we're going to have the same amount of each element on both sides of the chemical equation. That means I'm going to have the same elements on this side of the equation as well. And it's going to be helpful to just write them in the same order, even if they don't appear in the same order in the reverse side. So for example, here we have carbon and then oxygen appears next. But it's just going to be a little bit less confusing if we write it in the same order, whatever order we do on the left side, just do that on the right side as well. So let's go ahead and count how many carbons I have on both sides and how many hydrogens and how many oxygens. So we can count and we will see that there's a carbon right there. The carbons are represented by these black spheres. So we have one carbon on the left side of the equation. Let's go to the right side of the equation and see how many carbons we have there. I can count the black spheres, or I can count how many C's I see on in the chemical formulas. So there's one carbon on the right side, on the product side as well. On the reactant side, let's look at hydrogens next. We have 4 hydrogens. And those are a little bit harder to count when you're looking at the spheres because they're bonded to this oxygen and they're kind of hard to see. But we have 1, 2, 3, 4 hydrogens visually that we can see as well. So I'm going to write down that we have 4 hydrogens. And then let's look over on this side. I can count my spheres. I can say 1, 2, 3, 4 hydrogens. I can do it that way. But this isn't always going to be given to us. We're not always going to have a picture of what these different compounds look like. We are always welcome to draw what they look like, but on our own. But typically in a balanced chemical equation, when I give you a question, it's going to look like this. It's just going to be written like that. So a little bit less visual. But let's count how many hydrogens we have. So we have, like I said, when we count the actual numbers, when we count the visual representation of it, we said we had 4. But let's see how we get 4 when we're counting the number of H's that I have in the compounds. So no H's here, but when we go over here, we have 2 H2Os. All right. So what we're going to do here is we're going to take this 2 and multiply it by the subscript, and that tells us the total number of H's. And to make sense of that, what we have here is we have H2O represented by this sphere right here. We have H2O, and we have 2 of those H2Os. We have 2 H2Os. So I have H2O here, and I have H2O here. So I have 2 separate H2O molecules, and because of that, because each H2O molecule has 2 hydrogens, I end up having 4 hydrogens. So visually, that might make sense, but we just need to make sure that if we skip the visual, that we understand this mathematically as well. And we could say, well, for every H2O, we have 2 hydrogens, because this 2, the subscript always represents the number of the atom that's right next to it, that comes right before it. So each water molecule, H2O, has 2 hydrogens. Well, if I have 2 H2O molecules, that means I have 2 times 2, I have 4, 2 times 2, I have 4 total hydrogens. So again, I bet all of us can make sense of seeing that there are 4 hydrogens. But this is not always going to be laid out this clearly for you, as we'll see in the examples that we do even today. So we need to make sense of how this makes sense from given information like this. And so we have 2 H2O molecules, that gives us 4 total hydrogens. So let's write that down. 4 hydrogens. All right, moving on to our last element in this chemical reaction, oxygen. So same thing here. I have 2 O2 molecules. So O2 is made up of 2 oxygens. So for every one of these molecules, I have 2 oxygens. So 1, 2. And so we're trying to figure out how many total oxygens we have. So if I have 2 O2 molecules, that means I have O2, and I have another O2. So we need to count how many total O's we have, which would be 4. And again, probably really easy to see when we're counting the red spheres, which represent oxygens. But we need to be able to make sure that we know we can multiply this number by this number, and we get, or if multiplying is difficult for us, we can just say, well, we have O2, and we have another O2, because we have 2 total O2s, and we can just count how many total O2s we have, or count how many total oxygens we have, how many O's we have, from saying, well, 2, and then 4, and, you know, if there's no number written, then it's 1, however you want to do it. So, and then there's no oxygens here, so we have 4 total oxygens on the left side of the equation, on the reactant side. On the product side now, let's look. Well, I have some oxygens here. CO2 is made up of 2 oxygens. Remember, they're the red spheres, so we have 1, 2. And then H2O, well, there's some oxygens in H2O too, or H2O also. So oxygen here and oxygen here. So I have 4 total oxygens from that picture, and let's make sense of it from the from it written? Well, CO2 carbon dioxide is made up of, there are 2 oxygens in CO2. So there's 2 oxygens from that, plus there's more oxygens in another part of the equation. So I have every H2O molecule has 1 oxygen. We just don't write the 1 because, I don't know, we just don't. So I have 2 H2O molecules. So when I count the total number of oxygens, CO2, and then H2O and H2O, well, I have 2 right here, plus 1, plus 1. I have 4 total oxygens. Or I could say, I could do it this way. I could say I have 2 oxygens here, and then 2 times 1, so 2 more oxygens here. Or 2 times the number written in a subscript. There's no number in there because it's 1, so 2 times 1, so another 2 oxygens there. So we just need to, I'm just trying to emphasize this just because we need to be able to recognize things from it written, not always drawn, because it's almost never going to be drawn out like this for us. It's rarely going to be drawn out like this for us, and if it is, that's because we probably drew it out ourselves. And you guys are all more than welcome to draw out it if it's going to help you make sense of this a little bit more. I might even encourage that. We all have learned how to draw these chemical compounds, so it shouldn't be a problem if we wanted to draw these out, but that's just going to be an extra step. So let's go back and check our work. Well, I have 1 carbon on this side and 1 carbon on this side. So carbons are balanced. Check mark there. Carbons are balanced. Hydrogens, I have 4 hydrogens on this side and 4 hydrogens on this side. Hydrogens are balanced. And then oxygens, I have 4 on the left side and 4 on the right side. So oxygens are also balanced. So seeing that there are the exact same number of each element on both sides of the chemical equation tells us that they are balanced. Furthermore, this is a good example because it also shows us the mass of each compound in the chemical equation, written right here. So let's see what that looks like. I'm going to actually move what we just wrote down a little bit. Let's do that, and then we'll focus on this these mass amounts given and seeing how those balance. So let's draw our line again, and we have the reactant side. Actually, let's just draw it right here. Cool. On the reactant side, I have 16 grams worth of methane, but when we're looking at the mass, we're not specifically worried about how much methane, because we don't need methane on both sides of the equation. We just need carbons and hydrogens. We can break things apart, and that's what's happening in chemical reactions, the breaking and forming of bonds. So even though we don't have methane on both sides of the equation, we do have carbon and hydrogen. And those individual carbon and hydrogen atoms, they weigh the same amount, whether they're on the reactant side or product side. So anyway, we end up getting 16 grams worth of methane. The methane being irrelevant, we're just concerned with 16 grams, and then we're going to add that to the other part of the chemical equation. We have 2 O2s. Each of those O2 molecules weigh 32 grams. So let's add all this up, and we see that on the left side of the equation, on the reactant side, we have, let's see, 64 grams from here plus 16. So we have a total of 80 grams. So 16 plus 32 times 2 equals 80. So we have 80 grams on the left side of the equation. We have 80 grams worth of materials, worth of molecules and elements. 80 grams on the left side of the equation. Let's see how much we have on the right side of the equation. Once all the reactions have now occurred, let's see what we're left with. And we're going to add all this up. We get, 2 times 18 is going to be 36 plus 44 is going to be 80 grams. So now on the right side of the equation, on the product side, we also have 80 grams because we have the law of conservation of mass, where mass can neither be created nor destroyed ever, but especially in like a chemical reaction, we're always going to have the same mass on both sides of the equation, and furthermore, we're going to have the same number of each element on both sides of the chemical equation. So hopefully that was a helpful introduction to law of conservation of mass and balancing chemical equations. We see here that none of us are magicians. We didn't get rid of any oxygens or any carbons or any hydrogens. We can't get rid of them. We can't create them. We can't draw another one of something here. We can't create or destroy any elements or any amounts of mass. So hopefully that's helpful. We're going to do some example problems in our next video, so stay tuned for that.